All right, let's talk about the secret language that's running pretty much all of modern machine learning. I'm talking about everything from your spam filter all the way up to the most advanced AI out there. And that language, it's probability.
So let's just jump right in with the big question, right? How can a machine possibly learn anything when the data we feed it is, well, it's messy, it's incomplete, it's always uncertain. We're asking it to predict the future, to spot patterns, but we're giving it a fuzzy picture at best. How does that even work? That's really the core problem we're going to tackle today.
Okay, so the first thing we got to get our heads around is this thing called the uncertainty problem. It's really the biggest challenge in all of machine learning. The thing is, an ML model never gets to see the whole picture. Ever. It's always, and I mean always, just working with a tiny little slice of reality. And here's the kicker. We give the machine this small, known sample of data, we call it training data, and from that, it's supposed to understand this huge, vast, unknown world out there. I mean, think about that. How can you be so sure that what's true for your little sample is actually true for everything else? That massive gap between what we know and what we don't, yeah, that's pure uncertainty. But this is where our hero enters the story, probability theory. And look, don't think of it as just a bunch of scary, complex math. It's not. It's a language, a tool that humans have been perfecting for centuries for this exact problem. It gives us a rock-solid way to actually measure and reason about all that uncertainty we were just talking about. Okay, so here's where it gets kind of interesting. You'd think everyone agrees on what probability actually is, right? Well, nope. There are basically two big camps, two totally different ways of looking at chance. So on one side, you've got the frequentists. They think of probability as, how often something happens if you do it over and over and over again. Think about flipping a coin 1,000 times. Heads are going to come up about 50% of the time. That's the long-run frequency. But then you have the Bayesians. They see probability as a way to measure our belief or our confidence about something happening. This is super useful for things that only happen once. Like, what's the probability Brazil wins the next World Cup? You can't run that experiment 1,000 times, right? It's a one-shot deal. And that's exactly why the Bayesian way of thinking is such a game changer for machine learning. Come on, an ML model isn't trying to figure out the average of a million coin flips. It needs to make a prediction about one specific thing right now. It's all about quantifying a degree of belief based on the evidence it has in front of it. All right, enough theory. Let's make this real. We're going to look at something you probably use every single day without even thinking about it, your email spam filter. This is where all that abstract stuff hits the road. Okay, so here's the scenario. An email lands in your inbox, and it has the word bulk in it. Now, you know your spam filter is pretty good. It's about 80% reliable at catching spam. So what do you think? Is this email spam? I mean, your first instinct is probably, yeah, 80% sounds like spam to me. But you're about to be surprised. See, before we even look at the word bulk, we have to ask, what do we already know? This is what's called our prior belief. And the truth is, if you look at all the emails you get, real spam is actually super, super rare. We're talking less than 0.5%. That's a really important starting point. Okay, now let's look at the new evidence, the filter. Yeah, it's 80% reliable at catching spam, which is great. But here's the other side of the coin. It has a 10% false alarm rate. That means 1 out of every 10 times it screams spam, it's actually pointing at a perfectly good email. That's a huge piece of the puzzle. So, how do we combine our starting point, that spam is rare, with this new imperfect evidence from the filter? We use something called Bayes' rule. And again, don't get hung up on the formula. Just think of it as the engine, the logical recipe for updating what you believe when you get new information. It just mixes your prior knowledge with the new test results. And when you actually do the math, get this. The real probability that the email is spam is just 3.1%. That's it. So why is it so incredibly low when the filter is 80% reliable? It's because our starting belief, our prior, that spam is super rare is so powerful. A single piece of evidence from a kind of good but not perfect filter just isn't strong enough to completely change our mind. This is a machine learning. It's updating its belief in a rational way. Okay, that's pretty cool for one email. But what happens when a machine has to deal with, a whole data set? We're talking thousands, millions, even billions of data points. How does it start to see the bigger patterns in all that? Well, to do that, we need to introduce a key idea called a random variable. Now, the name is a little misleading.
It's not really a variable in the way you might think. It's more like a translator. It's a rule that just assigns a number to something that happens in the real world. Like saying heads is 1 and tails is 0. It just turns real-world stuff into numbers so a computer can do math on it. And these random variables basically come in two main flavors. You've got your discrete ones, which are for anything you can count, like the number you get on a dice roll, 1, 2, 3, 4, 5, or 6. Simple. Then you have continuous variables. These can be any value within a range, like the exact super precise time it takes someone to run a race. So once we've turned all our data into numbers, we can start looking for the overall shape, the big picture. And what's amazing is that a lot of data in the real world tends to follow a few common patterns. We call these distributions, but a better way to think of them is like blueprints. There's the Bernoulli blueprint for a single yes or no event, the binomial blueprint for a bunch of those events, and of course the most famous one of all, the Gaussian, or bell curve, which describes everything from people's heights to errors in measurements. Okay, so this brings us to the last and honestly the most mind-blowing piece of this whole puzzle. We've come back to our original question: how can a machine take a tiny little handful of data and make a giant leap of faith to say something meaningful about the entire world? That leap, it's not actually a leap of faith. It's possible because of one of the most powerful ideas in all of statistics. It's like a mathematical guarantee, the bedrock principle that says, hey, learning from a small sample isn't just a wild guess. It actually works. And that powerful idea is called the central limit theorem. It sounds super intimidating, but the concept is actually beautiful in its simplicity. Just picture this. First, you go out and grab a whole bunch of small, random samples from your big population of data. Then, for each of those little samples, you just calculate the average. And finally, you take all those averages you just calculated and you plot them on a graph. And here's the absolute magic trick. It doesn't matter what your original data looked like. It could be a total mess, completely random, all over the place. The graph of the averages of the samples will almost always form that nice, neat, predictable bell curve. That is why learning from samples works. It's that predictability. Now, to be clear, this isn't a silver bullet for everything. It has trouble with really rare black swan type events. But for most of the data in the world, this theorem is the mathematical backbone that allows a machine to learn from a tiny sliver of reality and still make sense of the whole thing. So let's end on this thought. We just saw how these basic rules of probability can teach a simple computer program how to filter spam, how to literally update its beliefs based on evidence. So now, just imagine what happens when you take those exact same rules and you apply them at the scale of the entire internet. Trillions and trillions of data points. What kinds of complex, incredible, maybe even scary behaviors can an AI learn then?